All right, welcome back, guys. This is Recitation 5 for MAE 242 Intro to Fluid Mechanics, as I'm sure you all know. Yeah, it's been a while. We had an exam last week, so as you all know, I'm sure. But yeah, so now we're back doing some new stuff. This is a pretty important recitation, honestly, moving forward. This is all about conservation of mass. Next week's will be conservation of momentum. And in my time doing this, I found this and momentum usually trip people up the most. So really, if you have any questions, feel free to reach out. This is kind of my specialty too. In the Aero program, you never really get away from stuff like this. So I've gotten this stuff down pretty well. But anyway, let's get into it. We've got 3 problems, and I'll outline each of them pretty well. I'll show you how to do all of them. But, the thing about these, once you get the tricks down, they're not too bad. So let's get into it. So for this first one, we have water flowing through point A at 60 kilograms per second. That's the mass flow rate. Then out of B at 4 meters per second. Or let's say 60 kilograms per second. I think I slipped up there. Then out of B at 4 meters per second. We want to find the average velocity at which it flows through point C. So I already went through and wrote down all of the stuff we're given. So we're given all of these values: the density, the mass flow rate at A, the velocity at B, and then the diameters we were also given. And so with that, since it's just circular pipes, right, I don't say it, but assume it's circular pipes, we can get the areas out of them, which is important. Now for the assumptions, these are really important, okay? These assumptions, we grade you on these on the exams. And, strictly speaking, if you don't make these assumptions, you can't really solve the problem, right? And you'll see what I mean, especially for the incompressible flow and the steady flow ones. Yeah, you'll see what I mean in a sec. So for the assumptions, we have that it's incompressible flow, okay? That just means that the density isn't changing, right? It's water. That's fine. Water's very incompressible, right? It takes a lot to compress water. That's why hydraulics works. Steady flow is our next assumption. And all that means is that nothing in this situation is changing with respect to time, okay? This control volume right here, right? Before I get ahead of myself, let's draw our control volume. In this case, it's easy enough. You just want to encompass this whole shape that we're dealing with here, right? Include all of the inlets and outlets, all that good stuff, right? So we usually denote it as a dotted box, right? Now let's do our normal vectors or unit normal vectors. And remember, a unit normal vector is just a unit vector, so it has magnitude of 1, and it is normal to whatever surface you're drawing it on. And by normal, we mean perpendicular, right? And it faces outward from all of your surfaces, okay? And so the points of interest we really care about are those ones right there. Okay, so back to the assumptions. So we drew this control volume, right? And we're saying it's steady flow. So nothing in this control volume is changing with respect to time, right? Of course, we have some velocities coming in and out and all that, but those are constant, right? Constant velocities, it's fine. Nothing, but if I take a picture of this and come back 10 years later, it should look the same, right? The volume's not changing either, so it's fine. Next, not super important for this type of problem, but I wrote inviscid flow, and that just means that we're assuming there's no viscosity effects going on here, which, that's more important in like a momentum situation. For mass flow, it's fine. Whatever. And then lastly, the last big one is uniform/1D fluxes at the inlets and outlets. And what that means is that there's no velocity profiles, right? You just have one velocity coming in, one velocity coming in, one velocity coming out. It's totally fine. And these velocities aren't at any funky angle, right? They're just coming straight in and coming straight out. They're not like cocked at any angle, right? So when you go and do your dot products and stuff, you just get a super easy number. So now with that, we can really start solving our problem. So let's go conservation of mass. And when you go and do this stuff, especially since you haven't done it a lot, try and write the base equations, like start to finish, right? Get those down. Get the basics down. So we got 0 equals our time derivative term of the control volume, rho dv. plus our control surface term, rho v dot n ds, right? So this is the control volume. This is the volume term, right? The time derivative volume term. And like we just said before, it's steady flow, okay? So you don't even care what's going on with this integral. You know that since nothing is changing with respect to time, whatever happens in this integral, it's just going to be constant over time. So what happens when you take the derivative of a constant? It goes away. So it's just cross that out. Now let's worry about this one, okay? This term right here. And this, for a very simple case like this boils down to a really easy answer, okay? So we know since it's incompressible, density is just constant. So let's just pull that out. That's totally fine. And then this v dot n right here, we're dotting a velocity vector with the unit normal vector, okay? Like I just said, in this case, since it's uniform and, uniform, 1D fluxes, right? Just have velocities coming in, velocities coming straight out. There's no profile. So this velocity is just going to be one finite number, right? It's just going to be one number going in some direction. And also, since it's 1D, right, there's no angles or anything. When we're dotting with this normal vector, it's either going to be cosine 0 if it's aligned, like in outlet case, or cosine 180 if it's against it, right? Which, what are those numbers? Well, it's 1 and -1. So this whole thing just boils down to v, right? And then this surface integral term, this ds, well, if it's just a nice, easy area, right? It's just a circle. You don't need to take an integral. You know what the result's going to be when you go and take this integral. It's going to spit out an area. Well, what's that area? For now, I'm just going to write a, but it's just going to be pi d squared over 4, right? It's just an area term. So that's what this boils down to in this super nice situation. So let's get going. So we're going to go 0 is equal to, now we need to analyze these terms, right? So I'm just going to go at point A, right? It'll be negative because it's coming in and you're dotting that VA dot N, right? They're opposing each other, so it's going to be negative. It's going to be negative rho VA. Then what's the, well, I'll just write area A. It's fine. Area A. And, that would be pi 0.1 squared over 4, right? Now let's do, and for these surface integrals, you have to do each interface, right? Each surface of interest, okay? So let's go to the other inlet, C. So minus rho VC, area C, okay? And again, that's because we're dotting that normal vector that's facing outwards with an opposing velocity vector, okay? And now last one, for B, it's going to be positive, right? Because we're coming out and we're aligned with the normal vector. So plus rho VB, area B. All right, so let's clean this up a little bit. As you can see, all these densities go away. And that's important too. That's from the incompressible assumption, right? Because we know it's just one constant density, all right? So that's pretty nice. So moving on, I'm just going to rearrange some stuff. So we can say VB AB is equal to VA area A plus VC area C. Or we're trying to solve for that VC. So now let's look at what we know. Well, we know the areas, right? Because it's circles and we know the diameters. We know the velocity at B, but we don't know A and C velocities. And we're trying to solve for C. But we do know that m dot, by definition, is rho VA. And what are we given in the problem statement? Well, we know that m dot A is 60. So just plug that in. So, and the density is 1,000. And the area is pi 0.1 squared over 4. So if you go plug that in, solve for VA, you get VA is equal to 7.64 meters per second. So now we've got everything we need. Plug everything else in. So we've got 4 times pi 0.16 squared over 4. It's equal to VA plus VC, which we don't know, times pi 0.06. Cool. So with that, boom, VC is equal to 7.22 meters per second. Not too bad. When you have a nice, easy one like this, it's pretty easy. The other ones get a little tougher. So let's move on to question 2 now, where it's a totally similar vibe, but instead of just everything being nice and easy 1D inlets, we have a velocity profile coming out. So we have a sheet of water with that density flows out of a nozzle with a narrow slit of thickness h. So this is a thickness h into the page, this little nozzle, with some velocity profile v of x. The velocity is uniform in h, and the water enters through a small pipe of diameter d. We want to find the inlet velocity u right there. So again, let's define our control volume. That's usually step 0. I apologize for kind of omitting that on the last one, but whatever. And again, this is just super easy one, right? This is like a sprinkler head sort of thing. Just encompass the sprinkler head. It's easy enough. Now for the normal vectors, right? It's just coming out of every surface. It's not that big of a deal. You get the idea. Okay, and so now we're given the density. We know the velocity profile. It's 4v x over L, 1 minus x over L, so it's some parabolic profile. The bid v, the bid, I assume that's the maximum velocity, right? The bid v is 5 meters per second. H, the thickness into the page, is 0.002 meters. The length is 0.2, and the diameter is 0.03. So again, the assumptions we'd make about this, of course, is water, so incompressible is fine. Again, it's steady. Nothing about this is changing with respect to time, right? You have a velocity profile, but that profile is constant over time, right? Nowhere in here is there a t mentioned. So again, you take a picture of it, come back later, it's going to be the same. The volume's not changing. It's totally cool. We'll see in this last problem when that isn't the case, what you do there. But for this case, steady, it's fine. Again, it's inviscid. But don't really care about that too much for this problem. And lastly, we have a uniform inlet, so that'll boil down just to the rho VA for the inlet, but we have a velocity profile at the outlet, so we're going to have to do something about that. So let's get into it. So again, always start with your basic conservation of mass. So we have 0 equals d by dt which again, it's steady, so we don't care about that term anyway. So let's just cross it out now before we do anything about it. Plus our control surface term. Right, and so now for this control surface term, all we have to worry about is the inlet right here and this outlet right here. So let's take care of the inlet, right? We have the velocity coming in here, u, and like we said, it's a uniform inlet, so this is fine. It's going to be negative because we're dotting it with the opposing normal vector. So it'll be minus rho u. I'll convert it. It's a circular pipe, so I'll just do it right away. That's the area right there. And now we know this outlet is at least going to be positive because it's always dotted with the normal vector facing in the same direction. So we plus some integral. And now, well, we actually have to do something with this integral now, but it's not that big of a deal. So you can look at this, equation and go, all right, well, obviously the density is constant, so that can just stay there. That's fine. And now instead of just having a finite number for this v vector right here, we actually have to do something with that profile, okay? But it's not all that bad because you can also look at this ds term, this surface term, and you go, okay, well, I know I'm going to have to integrate something with the velocity. So how is this velocity changing? Well, we just said up here, the velocity is uniform in h. So we can treat the thickness as a constant, right? And we know the velocity, the v of x, is only changing in this x direction as it goes with L. So we can simplify the surface integral into an h, a thickness, times dx. And we're going to be stepping with each dx, right? So we literally just sub that in. So we have our velocity profile times h, which is a constant because it's constant in thickness. It's only varying in the x direction. And how are we going to be integrating? We're going to be stepping in the x direction. So we're going to be integrating from x equals 0 to x equals L. All right, easy enough. So let's keep going. Let's plug it in. I'm going to move that over. Let's go rho u is equal to 0 to L of rho. And I know you can pull these constants out. I don't care. See what my profile will be. 4v 1 minus x over L h dx. Now literally just do the integral. I'm not going to sit here and do the integral for you. It's really not that hard. But, I would distribute the x over L into that and sub out the constant terms and it'd be pretty easy. So left with this expression right here. Should be 2/3 like LVH or something. Rho VLH. Again, pretty easy. It's incompressible, so those densities go away. And now we literally know everything else about the problem, so you can just sub in straight away. So go solve for u. We have u is equal to, multiply those over, divide that over. We have 8 over 3 pi d squared VLH, I believe. If my algebra is slightly wrong, whatever, the vibe is all the same. So plug in numbers. You know everything about it. You know diameter, you know velocity, the big V velocity. You know the length, and you know the thickness. So ultimately you're left with u is equal to 1.886 meters per second. Again, so that one still wasn't too bad. That's what happens when you can't just call everything 1D fluxes, right? Instead, a little more complicated, but really not too much. This is like probably the hardest thing you'll have to do. So I think you guys will probably survive. Anyway, let's get into this last one. Let me scoot the camera down a little bit. Sit in this last one. Hopefully I have enough room for it. It should be fine, but whatever. So this last one is what happens when you can't call everything steady, all right? So let's look what happens here. So we have two tanks. They're separated by a wall with a small hole right there. Water is flowing steadily through all 3 points of interest. At some time t, q dot 1, and I'll make that a little better. Q dot 1, the volume flow rate through point 1 is 5 cubic feet per second. The flow rate through 3 right here is 4 cubic feet per second. And the water heights are 15 feet and 12 feet, respectively. Both tanks have a width of 5 feet into the page. Part A, what is the rate of change of H1? Part B, what is Q dot 2 if the water in B is falling at 0.2 feet per second? So dead giveaway that we're not going to be able to cancel out the unsteady term, that d by dt term, because we know it asks us explicitly, what is the rate of change of H1, all right? So we're going to be changing with some time, okay? And so with that, we want to draw our control volume very carefully, right? You don't want to just draw a control volume around the whole outside of the tank, right? Because essentially when you draw a control volume, it becomes a black box, right? All you care about really is what's coming in and what's going out, okay? You lose the information of what's going on inside of it when you draw just a huge expansive control volume, right? So for this one, let's draw a control volume that just encompasses the tank itself right up to the height of the water. So now, when the water height changes, our little hypothetical water height that's changing, our control volume changes along with it. And with that, we can recover that volume term that's within the d by dt term. Cool? So again, I wrote some assumptions down. Incompressible, of course, is water. All the inlets and outlets are uniform and 1D. That's fine. Nothing too tricky there. Again, it's invested, whatever. But it's unsteady. Like I just said, it's unsteady. This volume will be changing with respect to time. So let's go ahead. Let's get our conservation of mass going. All right, now this, this whole term right here can literally just be simplified into m dot is equal to rho times q dot, where q dot is just equal to velocity times area. And that's just a convention thing. Like, that's just like a by definition. Yeah, velocity times area. That's how you get the cubic feet per second or cubic meters per second, right? Meters per second, meters squared, cubic meters per second, whatever. And so let's get going. So let's do the inlets and outlets first for this tank A. So we're going to have 0 is equal to, remember, dotting with our normal vectors. So we're going to have negative rho q dot 1, right, coming in. And then leaving, we're going to have positive rho q dot 3 going out. And now we got to do something with this time derivative term. So we're going to have plus, and let's think about what actually happens when we go and do this integral, right? So again, this is just a nice, easy rectangular shape. So we don't really need to do an integral, because you know what the volume integral for a rectangular prism is going to be. It's just going to be, length times width times height, right? So I'm going to draw it like this, d by dt, rho times some velocity, okay, where this rho is a constant, so we can drag that out. So let's do some cleaning up. So let's move those over. So we're going to have rho q dot 1 minus rho q dot 3 is equal to, I'm going to drag the density out of there, rho d by dt applied to some volume. So again, let's cancel that stuff out, easy enough. And now inside of this volume, okay, what is actually changing? What is changing over time? Well, we know it's not the length of it, all right? It's just a tank. The same thing, we know it's not the depth of it into the page, right? The width of it. Those are both constant. That's geometry. So the only thing that is changing is the thing we actually care about, the h1. So we can call this, we can do this whole thing and say q dot 1 minus q dot 3 is equal to length times width times dh1 dt. We're applying the time derivative term to that h1 that we're talking about, right? Literally, by definition, this is the change in h with respect to time. So go plug everything in. We have 5 minus 4 is equal to 5 times 5 dh1 dt. Solve for dh1 dt. This is, it's 1 over 25, so 0.04 feet per second. So there's that one. Now for part B, it's literally just the same thing, but in the opposite direction, so I guess I'll do it. So what is q dot 2 if the water in B falls at 0.2 feet per second? So we'll have dh2 dt is equal to negative 0.2, right? It's falling. And so we're going to have, so in this case though, now Q3 is the inlet in this other case for tank B. So we'll have Q dot 3 minus Q dot 2 is equal to, our length here is 8 times 5 times negative 0.2, right? Q dot 3 is still equal to 4. So plug in, you get q dot 2 is equal to 12 feet per second. Cubic feet per second, sorry. Boom. So there's that. And just a sanity check, right? Well, if you know tank B is falling at some time rate, right? Obviously q dot 2 has to be greater, right? It's coming out, has to be greater than what's going in, because obviously the tank is falling, so that's good. And also you'll notice the water heights h1 and h2, we don't actually care about what those actual heights were. Those just kind of throw you off. When you're dealing with rates of change, you don't necessarily care about what the initial value is, right? When you do the derivative of it, you lose that initial value anyway. So anyway, that's that. Yeah, and the control volume for part B would have just been same thing, but with tank B. Get the picture. Yeah, these can definitely be pretty tricky. Mass itself isn't too bad, but once you couple it with momentum, things can get kind of complicated. But yeah, that's that. If you guys have anything else you need to let me know about, put in the comments or email me. But that should be it. Have a good one.